Sampling design. In this class, we will go over some key concepts, and your final exam, I will ask you, what concept name, and sometimes let you choose appropriate terminology. Sometimes let you choose filling the, sentence, and sometimes I ask you briefly describe two or three sentences about the concept, right? So understanding concept, vocabulary, taxonomy is very important. And then we're getting into simple random sampling. And then after we finish this simple and random sampling, we're getting into more like a complex sampling design. Sometimes we call it a multi-stage sampling. And then last point, and we will talk about determining sampling size. Okay, how we making a decision about the sample size, right? All right. First of all, let's review key concepts. And first of all, we already did it. Sample and population. Sample is a subset of population, right? And sampling means the process of getting subset out of the population. Sampling, right? And in when we talk in research design, randomization is very important. Random is very important concept, right? And we use this randomization in two different places. Number one, when we randomly sample, we use randomization process. And previous lectures, we talk about experimental research and randomized control design. In that case, we use random assignment. So random selection is different from random assignment. Random sampling in this class make it as the same concept as random selection and sampling is the same thing, right? Slightly different, but let's pretend the two things are same in this class, right? And we will talk about this issue many, many times. To implement random, we need complete list of subject respondents with population list. Sometimes we call it a population list. We need to have a list. And then randomization tool. Randomization tool nowadays relatively easy because you can use Excel, SPSS, and software, rolling a dice. There's a reasonably accessible randomization tool, but the most important and also challenging part is getting that list of subjects. So look at this. If you have everybody's name on the hat, random selection is very easy. But again, if you are interested into sampling 50 students, randomly select 50 students from DC third grade, high schooler. If you just find out any 50, it's not a random sample. And if you want to make it as a random sample, you need to have a complete list of third year high schooler, and then you have to randomly select out of it. Having that complete list is daunting task, sometimes impossible. Very challenging to have it. If you are hired as some evaluator, and but you're really interested into what America think about this actor, right? Hey, how you get the complete list of America, right? That reason my random sample from America is very, 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 very challenging. How about that? That competition, voice competition. So Voice of America, right? And then we are participating that Voice of America by apps, right? But they're gathering data, reasonably large of data, right? Tons of hundreds of thousands of the data they will collect, right? That is Voice of America, right? But it's not random Voice of America. Are you with me? Because we are not select their opinion from the complete list. Those respondents are what? They choose, they participate. It's a bias, multidimensionally biased. That voice is very biased voice from America. If you, I know it's a, we are not talking about that data is a fake data, but we are talking about what those if those things are not random, it's not representative. So we talk about what not strong generalizability. Another name of generalizability is what external validity. There you go. So sampling design is primarily interest in sampling design's primary interest is about the generalizability, external validity. Experimental design, their primary interest is what? Internal validity, causal inferences, right? Sampling design is primarily interested in that external validity, generalizability. Random sampling, again, we need to have a list of population randomization tool, right? And we already talked about those things. Again, randomly select is not no reason I will do it whatever I want. It's different from randomization in stat and quantitative research world, right? It's very scientific probabilistic sampling method, right? When instead of sampling, random selection, random assignment, we already talked about it. Researcher create experimental variable, and then which is typically control group, experimental group type of thing, right? And the random assignment is given sample. Most of case with given sample, right? And then we randomly assign those sample into treatment group and control group. So but before we learn this sampling design, we didn't describe where that sample came from. Basically, this and sampling design, we cares about how those samples were selected from the population. Okay, the key interest in this step is generalizability. Key interest of random assignment is what? Internal validity, causal inference related to independent variable and dependent variable, specifically experimental variable. Okay. Another very important concept of terminology is sampling variation. Sampling variation. Sampling variation is variation in a statistic from sample to sample due to random sampling fluctuation, right? Okay, let's talk about this. We need to do a couple of more steps. Given population, right, and high schooler in DC, you randomly select 50 students and then compute average of their SAT score and write down that average in here. You compute the mean, you compute variance, right? And given that 50 students, are you with me? That's a first sample statistic. For example, average of first sample, 50 students. And you're not stopped there. You go ahead to select again another 50 and then compute the SAT score out of the second 50, but randomly selected the second sample. And then compute the SAT score. And then write down. And then do it again and again. Are you expecting those sample averages? All right, you got to average it from the first sample, second sample, and third sample, right? Those things are statistic because that's a characteristic of sample. We call it statistic, right? Are they same? Why not same? Because that came out from the population, same 50 students. Why average of the first 50 student is different from average of second 50 student? Because those 50 students are randomly selected. So there's no guarantee second sample average will be same as first sample average. But they're similar. Why? They will be similar. Why? Hmm? Because we randomly select from the population, yeah, like a DC average, right? But only 50 students. Accidentally, you choose smart kids. Accidentally, you choose not smart kids, right? And average will vary because of the method you select is what? Randomly, random selection, right? So variation, listen carefully. Sampling variation is variation of statistic across samples. This is like a weird situation. You're doing sampling many, many times. Again, variation in sample statistic, which is average of each groups out of the potentially out of many, many samples. Oh, Dr. Troy, I never thought about that kind of situation. I just collect one time. Why we need to think about collecting many, many times? Because the the sample what you got is one case of potentially many samples, right? Again, that is definition. Again, sampling variation is this first sample mean is different from the other sample mean, right? They are varying. The reason of varying is what? Because of the random selection, random sampling. Good question. Good question. Right? How our book described it, the size of variation is function of sample size. If your number of sample is getting a bigger and getting a bigger, and then at some point you collect every DC high school students, now that's the largest sample ever, right? What is the scenario? The situation you collect everything. We call it as CECENCENS census. We call it as a census. If you collect your sample equal to population size, it's a census. You collect everything, compute average, and collect everything and compute average. You keep doing over and over, the average won't change. Variation will be reduced down over sample size. Sampling variation is inverse function of sample size. Are you with me? Even though you collect the data from the given population DC, if your sample size is only 50, it will vary much more than 50,000 or 5,000. If you collect the 5,000 random sample out of the DC high schooler, compute the SAT, that's much more stable, was not very much over sample. 5,000 average is very similar to another 5,000 average compared to 50 sample, right? So our book describes in that relationship. Okay, that's a great question. Another definition sampling error is you know, there is a population mean, right? What do you mean by population mean? Average of every high schooler. And then there is a sample mean. What do you mean by sample mean? Average of given that 50 or 5,000 sample. And the deviation between difference between population mean and sample mean, we call it as sampling error. But that one is not we directly we cannot observe that one because we don't know population mean. We try to estimate population mean using sample mean, but in statistical process we can estimate that sampling error, right? So again, why two things are deviate from each other? Because my sample is random sample, part of information. It's not a, it's imperfect information, imperfect data. Population mean is what? Perfect data. You got you're the God. You know everything. Because you can compute the average out of the thing you know everything, right? But we are human being. We always working with imperfect data. So, but we try to estimate those population mean using sample data. But deviation between sample mean, right? On average, deviation from sample mean to population mean, we call it as sampling error, right? So in this case, you can compute two. Population average is 10, sample average is 8. You can compute deviation as a 2, right? But what if you need to do it this sampling many times? What is average of deviation between sample means to population? That is definition of sampling error. Again, one time sample you can just compute population mean minus the sample mean. That's not an error. That's just subtraction between population mean sampling mean. If you do it many times, what is average of deviation between population and many sample means, right? That is concept of sampling error. I know in this class, let's just define as difference and deviation from characteristic of sample and characteristics of population, right? Sampling bias. Another good vocabulary, sampling bias. Sampling bias is distortion between sample mean, sample characteristic, and population characteristic because because you choose a particular method. So sampling bias is what? Very bad. We like to eliminate. Sampling error is what? Always happening. It's not a bad thing. It exists. It's randomly, there's some random deviation from your sample, a particular sample to the population, right? It happened because of random sampling process. But this is bad thing, evil thing. Why? Because you choose particular method to participate, collect data. They start to distorting, right? Distortion of what you like to measure and what you measure. For example, and then you are hired to measure students' opinion about a particular policy. And then you decide to collect the data and in from the university library, right? And then you decide to do well. A lot of people being around there to 11 a.m. to 3 p.m. So you spend what 5 hours and 4 hours to data collection in front of library. Lots of traffics, right? But what happened? And then you summarize result, right? And then you like to present that one. And what's the biggest concern about the way or method of your data? That data you didn't cheat anything, right? Right? You didn't manipulate anything, right? But there's a serious concerns associated with data collection in terms of generalizability. Why? Because you choose 11 to 3 p.m. in from the library, right? And if you like to generalize that result to entire, you know, um, school, I mean, entire university student, opinion, it's to systematically exclude full-time students, graduate students, off-campus students. Are you with me? Systematically, because you choose that method. So there will be deviation between true population opinion and the data, your data opinion, right? And then we call it as a sampling bias. That deviation came out from what? Systematically from where? The method, sampling method you choose. The details of those sampling method you choose, creating that distortion. We call it as a bias. Instead word, bias is very bad. Instead word, error is okay. We understand that there might be some error because we understand imperfectness of our side. But bias is a systematic deviation. Error is what? Random deviation due to randomization. Deviation due to average deviation due to randomization. Bias is what? Systematic deviation because of a particular choice. We don't like it. We like to eliminate the bias as much as we could. All right. Again, sampling bias, sampling variation, sampling errors are all different concept vocabulary. Very important. Right. All right. Let's getting into simple random sampling. There are several type of sampling method. Sometimes we call it sampling methodology, sampling design methodology, right? Obviously, there is a simple random sampling (SRS), and then also, as opposed to simple random sampling, complicated, complex sampling method, random sampling or non-random sampling. The first one is stratified sampling, and second one is cluster sampling, and third one is a systematic sampling. We will talk about those. Basically, how many sampling method we will review in this class? Four different: simple random sampling, stratified, cluster, and systematic. All right, simple random sampling. Simple random sampling is you randomly select subject out of right given number. Like, oh, I want to select the four out of this population, and each subject in the population had exactly same percentage of being selected. For example, I had 60 student in this class, right? I want to select 10% of this 60 student, which is a 6 student, right? If I decide proportion, right? Fraction, right? Fractions. And then those fraction becomes what? Probability being selected. So everybody got ahead of what? 10% of chance to being selected. So I can easily create, you know, 1 out of 10 random, generator. And then I can select 10 students out of this 6 students out of this classroom, which is 60, 10%. Again, to do it, I need to assign equal probability. I have to determine that chance to being selected for each one, and I have to exercise that percentage for everybody. All right, it's very easy to do, right, and easy to understand. Most of random selection is falling in this category. Are you with me? All right. So to do it, the step-by-step procedure for simple random sampling is, first of all, you must have a population list. Again, we need to have a list, names onto our head, right? We need to have everybody's name, and then we deciding sampling fraction, 20%, 30%, whatever appropriate to our research design, right? I want to have a 20% of this population. Typically, we go over to target sample size because I want to collect 40 students out of I want to collect at least 500, right? And then you need to assigning certain amount of proportion fractions to being selected. And then once you determine that sampling fraction, 20%, 30%, and then you need to have randomization tool. Again, nowadays so easy. Excel, Google, and then let you do random number generator is everywhere, right? Traditionally, it was very tough to have that pseudo random number generator with you, and people we need like a random number table, and sometimes the library they publish those random number table to let us to do some randomized control design, random selection or random assignment, and both of them. But nowadays it's so easy. Even Excel did a great job to select SPSS and website. There's a couple of website doing lots of different type of randomization techniques you can easily apply. All right. All right, simple random sampling is very simple, very easy. But what is most biggest challenge in this process? Again, get, secure, identify, have population list. Where is a population list? So in the example of data collection in front of Gell-Mann Library, University Library will be what? How you can save that research? You need to go to where? Instead of Gell-Mann Library. You have to go to Office of Registrar and then request what? Complete list of students in GW. And then you randomly select out of those students to collect the data. That becomes what? Simple random selection process. Are you with me? So you need to have access to that complete list of population you like to generalize. Population is the group, whatever you extend to generalize. It could be third grader. It could be, female students in, in fifth grade, or it could be, every United States, elementary school. It could be every students in United States in the world. So choose the largest set you like to generalize your conclusion. That is a population, right? So again, it's very tough to have those complete lists and get access, even though you have a list to get access those subject to collect the data. So those sampling methodology has been developed to make it rigorous as possible. Focus on what? Generalizable as possible, and then also as practical as possible. It should be doable, otherwise impossible to do it, right? All right, complex sampling methodology, which is multi-stage sampling. As opposed to simple random sampling, not every data is as easily to collect as a simple random sampling. People start to figuring some more complicated, sampling methodology. Number one, and when we need to think about beyond the simple random sampling, the first scenario, if a population is too big, there's no way to get complete list of population. Even you have a list and you don't know where are they. So the data collection is nearly not possible. Even though you have a name, you don't know where are they. Because you don't have a context, you can't make that, participate, etc., right? Number two, population is very diverse and then decomposed of the several subpopulation, right? So we call it as what? And then you really want to counting those heterogeneous subpopulation. Most of the population is naturally grouped or clustered. But it's a great example if you decide to understand opinion of America, right? What is a natural group of Americans? States. Why? Because just people choose to which state they live, right? State resident, right? I believe every American need to have a state residency, right? Because United States of America, right? Are you with me? And or clustered. Geometric data. Geometrically, we are human beings, especially human beings. We are bounded to where we live. Okay? So, and those things are already determined for some extent. If you want to working with to your school district, what is the natural group they already cluster on your students? Schools, right? Your students are clustered and nested within schools automatically, and each school clustered in classroom already. So you take advantage of those schools and classroom, those already existing group or clustered, right? Subpopulation, subgroups, right? Um, um, in data collection. Criteria for designing sampling method. So what is good criteria to designing sampling methodology or sampling design? The first one is, especially simple random sampling is so easy. Okay, I like to generalize to the population and goal oriented. Are you interested into group differences? Are you interested into generalize to state as much as you could, or you more interested in school level, right? What kind of subgroup you're using it, how many nested structure you're using it, need to consistent with what, need to be consistent with what the goal orientation for your research is. What research question, what research question you have, and also focus on what generalizability, how in what group you real mostly generalizable, and what group contrast you really maximally detect. And then that is actually what seriously related to how you sample your data. Choose multi-stage method. And the second one is measurability. It should be measurable, right? And if you decide to choose a student achievement, right, it's not measurable. If you choose different school district, why? Your dependent variable, operational definition of your dependent variable, is very different from school district A and school district B. There's not so much comparability, and school district A is possible to measure parental perceptions to your to school, but school district B, some policy region, another region, it's not possible to measure, right? So in that case, choosing what kind of design, sampling design, is related to feasibility of your data collection. Of course, practicability sometimes take too long, right? And sometimes it's not possible to do it. Practically not possible. Very hard. And economy, money, money, money. Not only money, but also what? Time. Yes, time. Time equal to money in research world, especially data collection assessment. It takes 2 years. Sorry, it's very expensive. The process times take too long. It's just turning into what? Expensive process. And then also you need to do what? Balance out of those criteria. It should be generalizable as much as you could, have to be measurable as much as you could, and need to be practical as much as you could, and need to be what? Economical as well. So it's not easy to do if you like to interested to conduct regionally large size research project. Even though your final project proposal, you don't have to worry about money, but you should articulate these kind of conditions and criterion to you justify your sampling design, right? Like a checkpoint. Evaluate your self evaluation about your sampling design. The first multi-stage or complex sampling design is stratified sampling. Stratified sampling is you divide, first steps, you divide entire population into two or more subgroup. Now that subgroup, let's call it the strata. Still subgroups. Entire population decomposed into 5 different groups. And then each groups you select, for example, 10%, 5%, or 50%. One more time. Once you decide cluster, after you separate your entire population into subgroup, we call it as strata, and then you select 50% per each strata. So 2 out of 4, and the second group what? The same as 2 out of 4, and then third group what? 1 out of 2, and fourth group randomly select 2 out of 4, and second group is a 1 out of 2. Last group, fifth group. Are you with me? So the first step, you don't do any randomization. What you do is what? Decompose into entire population into subgroups. And then every group, every subgroup, you do random sampling, like a simple random sampling and given percentage. In this example, you applied what? What was the sampling fractions? 50%, 0.5, right? 50% of the data you will collect in each cluster. If this is your school district and this is a hypothetical scenario, how many schools you have it? And then if you decide to school as a subgroup, how many schools you have it? For example, in this case, 5 schools, right? And then each school you collect 50%. This is a stratified sampling process. Yes. Choose fraction and then apply that simple random sampling process for the every. This is like, some upgraded version of simple random sampling. Uh, hmm? Yeah, proportional allocation is like a 50%, 50%, 50%. You choose what percentage you need to do it. Mhm. Mhm. No, same proportion for each one. 50% from school A, 50% from school B, right? Doesn't matter school size. We decide to do the same proportion, simple random sampling proportion for the each subgroup, i.e., strata in this case. All right, cool. So this is example. If you want to have like this is like for example this is nationwide and school of education, and then we have we got a 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 different type of measure, right? And educational measure becomes strata, and then you decide to sampling fraction as zero point 0.1, which is 10% for some reason, right? So each strata you select approximately 10% out of it. Okay, so this is procedure how you do it. Okay, measure as subgroup strata in this case, and you apply the 10% for the each strata. So this number should be approximately total sample size should be approximately 10% of the entire population size. Why? Because each group you applied 10%. So total sample size, sum of all each strata sample size need to be approximately 10% of the population size. Any question? Now, you can do you can do more complicated one. Like for example, previous example, you can further decompose into graduate and undergraduate. So given major, you can have a graduate program and undergraduate program. You can separate those things into proportion and apply, and it becomes a little bit more complicated, right? But you can, as long as you do it, what happened? It's getting tough to implement, but it's more generalizable. And then you estimate gender ratio, and then you're also using gender as additional strata, and then your gender factor becomes what? More representative. If your strata size fraction is too small, sometimes you collect the data for every female students, every Asians, right? So make sure a certain group were collected as representative as possible. Like a Delaware. See, Delaware is a very small, but we want to make sure Delaware boys is coming into my data collection, right? If you choose, just very simple random sampling, a lot of boys, you know, if you don't have a reasonably large sample size, Delaware will be likely ignored. And a lot of boys, random boys, came out of from where? California, maybe. If your sample unlucky case, if your sample size is too small, right? Representativeness is what struggled. In that case, you make sure to creating strata. Why? Because if you choose those Delaware, even 1%, 2%, make sure 1% of the data set from Delaware. Otherwise, there's no guarantee. If you do the random sampling, there's no guarantee Delaware data will coming into your data set. You understand what I'm saying, right? So strata sampling is very popular because it's intuitively easy to understand how those strata boost up those generalizability over simple random sampling case, right? Cluster sampling definition. Cluster sampling first step is exactly same. Decompose your population into subgroups. And then you randomly select those subgroups. You call it as cluster. One more time. You randomly select cluster. And then once not selected, you just ignore. It being selected and collect every data. So this is what very, very convenient than stratified sampling practically. Why? To do stratified sampling, you have to visit every state. Are you with me? But in cluster sampling, if you okay, there's a 50 states. Let me just randomly select 10%. Random selection process for the selecting states, right? And then you visit only what? That those 10 states. You don't have to go everywhere. Very practical, but is very less less representative than stratified sampling, holding all things constant. Less representative. So that is the reason why stratified sampling is more popular than cluster sampling, by default. And another downside is it's tough to control total sample size. See, think about this. You decide to randomly select states, right? What if you select California? What if you select Delaware? See, out of the 10 states, it really depends because your cluster size is very different. If cluster size are very similar, it doesn't matter. Total sample size will be eventually is very similar, and what type of 10 cluster you will select. But cluster size is we call it unbalanced, very unbalanced. Each clusters are very unbalanced, and you don't know how many samples you will eventually collect because each cluster size is so different. And which cluster will be selected is don't know. It's randomly selected. Right? That's the reason why less popular than cluster sampling is less popular than stratified sampling because of two reasons. A little bit less representative, and then also not easy to control total sample size. You can extend that one, right? And or you can combining those stratified sampling and cluster sampling. If you cares about generalizability of America, I want to go for the first level. I mean, highest level, which is state level. I would like to choose what cluster or stratified. Stratified. Why? Because I want to make sure to every state's voice coming into my data set as proportion as their population, right? Number one. But given state, I'd rather choose clustering for 50 school district I like to choose. Why? Given state, 50 school district is okay enough to me. I don't have to visit every school district in given state because within state I less care about. I'm more cares about what across state comparison, entire America voice, right? And then given state, school district select and how you choose. stratified or clustering or your school district as school, given school district, it's also another, you know, cases. I mean, it depends on research question. If I were you, my biggest goal is generalized to United States. I will definitely choose stratify the sampling for the state level, but and then I will go for the cluster. I will randomly select 30% of school district, and given selected school district, randomly select 30% of schools, right? Why? Because I don't want to visit every school. School size are reasonably similar, right? I don't have to balance all those school size, everything. Holding other things constant. Of course, if we have infinite amount of money, right? We collect everything. But if I have to choose those different layer, different levels, right? And we can justify those method according to the biggest important thing is what? Generalizability, practicality, measurability, and also what? Economic reason. Money. How long are we gonna take to collect all that much of the data set, right? So we that you know you know all those consideration make your study is more thoughtful. Again, the cluster should be clear, right? But in not as sometimes it's not as clear as what school district school. So ethnicity. Sometimes, oh, what do you mean by ethnicity? Sometimes people disagree about ethnicity. Sometimes they disagree about gender classification. Lots of classification people don't agree about it, right? So clear definition of clusters of population is very important. Right? So, and then also you need to think about how to utilizing those. What is impact of those choosing cluster? What type of cluster? Will related to what type of your research question and research method as well. There are many research methodologies, like you analyze those different groups, right? Analysis variance and multi-level modeling, HLM, random coefficient modeling. There's a many different type of methodology let you analyze those clustered nested hierarchical structure of the data set. Okay, question? Mm-hmm. Well, in yeah, but this is more like multi-stage cluster sampling. The first one is see, I randomly select states, which is what cluster, and then also given states, I randomly select cities, the cluster, and then randomly select schools cluster, right? Because I'm not visiting every schools. I just randomly select schools and then randomly select students within school. That's it. Still cluster, which I consider. Yeah. And then in this case, and the last step is interview all students in that school students. I'm randomly select students within. Okay, when I'm sorry, stage four, given school selected, I randomly select students out of like a 20%, 30%. I think the last stage is very similar to stratified, right? I agree. I agree. Not every student, right? I decide to 50%, 40%. I don't know how to say that last step is stratifying the sampling. Still, even though this is a little bit deviation from the typical definition of cluster sampling, once you decide group, collect everybody, right? In this case, I may have a 50%, 40%, 100%. It depends on me, right? I mean, it depends on research design, right? But I will argue this method is still cluster, multi-stage cluster method because I didn't visit every schools in here because I just select schools and then certain percentage of students will be selected out of each school, right? But again, this diagram image is different from this combination, two techniques, stratified and cluster sampling. If you want to make it as this one as a combination between cluster only and difference between cluster only and stratified and cluster, I will go for this one. And I will make it as the stated strata. I will visit every state and then randomly select cities and next step. And then that becomes a what? This stage becomes stratified sampling and next stage becomes cluster sampling. Are you with me?
I mean, I don't know. I think I'm messing
Mm-hmm.
around.
Mm-hmm.
But like, if you cluster
Mm-hmm.
your states and then you do stratify, if you cluster, stratify, cluster, stratify, could you do that? Like,
Sure, why not? I can stratify it in here, and then once I decide to visit to every state with a stratified, and then what? Make it as cluster. Choose particular, you know, county. Not I'm not visiting every county in each state. I randomly select 50% of counties, which is cluster, and then each county I will visit every school. You understand? Now strata, every school, and then every school I decide to collect 30%, 10%. So now becomes strata, cluster, strata. Again, it's just all about, so those combination need to be made by those multiple criteria: money, generalizability, feasibility, etc., etc. Big study, right? And a lot of experts and engineered those different large scale data analysis and longitudinal and the big and large scale data analysis for monitoring and evaluation what's going on in the United States. Ad policy and a lot of public health policy, right? Series depends on those multi-stage data collection method. So we need to understand how those data were collected and what mechanism of their generalizability, or strength of generalizability of that data collection method possess. It's very important for us to understand, right? Okay, great questions. And systematic sampling definition is a very convenient way of dealing with large population with older the lists are available. For somehow some extent, there's older people list and older the list. And then you choose every third subject to select 30%, every fifth subject to select approximately 20% randomly. See, this type of method is works, but it there's order is just not so much meaningful. There's a there's a reason why people put that order, right? And this method is very dangerous to create bias because the reason why they put that order, right? So one of the easy way of get rid of that ordinality on our human subject is what? Oh, those names are ordered by alphabetically. See, we oftentimes we create order of those list, making a list of the subject by alphabetically. Why? Because alphabet not tell them their ethnicity much, not tell them their social economical, not tell them much about what their gender. I believe so. I'm not sure of the America case. At least another, Korean names, not alphabet, doesn't tell us much of information. But be careful. Who knows? In America, alphabet order seriously biased to gender. So a lot of A's for the girl's name or the other way around, right? So be careful how those order were created. As long as those orders are no region, no systematic, reason those order We call it not bias. And these methods start to approximate random selection. This process is what as easy as what random selections, like a simple random sampling method. Very similar. Especially peoples are coming like a sequence. Instead of you got like an entire population, you cannot select. So if you're working in your a research lab, like a counseling lab, and you want to collect the data 30% of your counselee, and what you can do, every third clients and start to collect the data. That works. Why? Because you can't just everybody coming in select, because that's a population. Population is what entire counselee, but you can approximate the 30%, and every third person you start to collect the data and start to mimic those random selection. I'm sorry, random selection process is very very clever way of doing it, but still dangerous, right? So periodicity. There's no repeatedness in that order, right? Make sure. All right, periodicity is threats of that this systematic sampling. But again, this is very, very convenient tool to approximate simple random sampling. All right, next one is sample size determination. Sample size determination is how we determine how many sample, right? Number one, statistical power and precision. And I will call it as a statistical conclusion validity. One more time, statistical conclusion validity. If you have a too small sample size, you have a too little statistical power, and then you don't have enough power to detect differences or significances. But I want to emphasize this one, not just boosting up statistical power. We will talk about statistical power later. Is how much you can make correct decision. For now, just statistical correct decision. Percentage of correct decision when your null hypothesis is false. But again, we didn't learn null hypothesis, alternative hypothesis yet, except some student took 6116 before. All right. But again, if you choose a statistical analysis, there's assumptions of statistical analysis. If you have a very small sample size, let me tell you this, you are not robust to violation of those assumptions. You're very, very what? Influenced by violation of assumption. Which is if you ever violate assumptions, your conclusion is inaccurate. So statistical conclusion validity becomes weak if you have a too small sample size, period. Because of statistical method requires reasonable and met assumption, right? If your sample size is too small, you are not robust to violation of assumption. So minimum sample size always you have to concern. Are you with me? But that depends on what type of statistical method you are choosing it. What type of data you have it. How complicated, how complex your research question is and statistical method is. It really depends, right? And also to determine sampling size, effect size should be determined beforehand. Effect size is what? Some strength of association between, like a normalized, standardized strength between your independent variable and dependent variable. When we talk about inferential statistic, we'll be getting in more detail about effect size. But where that effect size, how those effect size can be determined, the best way of determining effect size is literature review. You have to find out other quantitative research with similar independent variable and dependent variable. In APA requirement, we must report the effect size for the nearly every quantitative analysis. One more time, we need to report effect size. So we can guess, we can estimate appropriate size of effect size from my future study. From where? Literature review. Because most of quantitative literature review required to produce that effect size. Effect size, some comparable strength of association, strength of effect, right? Like sometimes percentage ratio, right? Cohen's d, r square, eta square. It depends on statistical method. We don't want to get into much details about those definitions of effect size. But again, to determine sample size, we need to have expected value of effect size before um, to understand, to estimate sample size requirement. Number one, again, let's summarize why we have to, what kind of, and then factors. I mean, last one, factors, cost, money, time. Money and time. Data collection costs a lot of money and time. It's an expensive process. So this is like a practically you have to choose, right? General guideline for determining sample size. If you have a more variable, more independent variable, for example, oh, I'm gonna adding this one into control. I wanna adding this one for what? Experimental scenario. If you have a more variable, your model gets more complicated and requires more sample size, more data. Otherwise, again, as I told you, statistical conclusion validity is a statistical method. It's good to choose complicated model, collect a lot of variables, right? Variable is what? More like column, right? But if your row is not enough, you have a lot of research question complication on over amount of evidence, empirical evidence, and your models start to behave what it won't work much. At some point, what you're even though you draw some conclusion, statistical model give you some conclusion, but that's not very robust to violation of assumption. Inflated type 1 error rate, inaccurate standard error rate, and we will talk about those issues later. But again, statistical conclusion validity is weak. So holding sample size constant, what you need to do? Simplify your model. Right? If you have a too small sample size, first thing you have to considering is what? Simplifying your model. Holding your model simplicity as a holding your model is very simple, right? And then if you increasing sample size, what you gain? Statistical power you will gain. You have a more accurately, rejecting null hypothesis when null hypothesis really false. And then the most important thing, and then of course your sample need to be as random as possible, right? If you have non-random sample coming in, you start to your convenience sample or non-random sample reduce down your generalizability of your study, right? So as random as possible. Last one is this. Oh, Dr. Choi, I can use the tax dollar to collect data, right? I got a lot of access to the data, right? If you nowadays people are seriously concerning, especially 21st century, too much sample size. Conventional statistical analysis, you can find extremely statistically significant, however practically insignificant result. One more time. And because if you have a lot of data, we call it a statistically overly powerful. Statistically overly powerful. You have a very statistically significant, but practically nothing. You can improve only zero point 0.3 SAT score, zero point 0.3 GRE improvement, If you have a lot of data, stupidly lots of data, you can make only zero point 0.3 GPA improvement can be very statistically significant. But practically, zero point 0.3 GPA improvement, who cares? Right? It's not that much big deal practically. But you can make it as a what? That small practical improvement, you can make it as statistically significant by having too much sample size. Again, that's the reason why you need to have a lower boundary, minimum sample size, to maintain statistical conclusion validity. And also, we recommend do not collect too much data for go green, and then also what? Your statistical analysis becomes not informative if you have too much data set, especially this conventional hypothesis testing, statistical hypothesis test. You can reject nearly every you know um, null hypothesis. So you basically a priori sample size determination processes provide the range. I like to collect data at least this much to maintain statistical conclusion validity, minimum sample size. And I don't want to collect data more than this size because from here becomes overly powerful. So now your sample size collection range, aim, target range could be 300 to, like, for example, 300 to 500 is enough. That kind of analysis, like a range analysis, sample size collection range analysis becomes what? We call this a priori sample size determination. It's a money. Why? Because scientifically you can ask, oh, like sample size is money, right? So good prediction to saving your research as rigorous as possible and not spending too much resources, right? People are recommending that analysis strongly in any, intermediate or higher study. Go ahead.
You were saying that we get the safer sample size via our literature that we would do for question.
If we do the lit review, we are hunting effect size for the other study. And then combining those effect size, we are using that effect size as my effect size. And then we decide the research method, some regression analysis, and each statistical analysis they have their own way of compute sample size requirement. We call it the a priori power analysis. Exactly same as what? A priori sample size determination process before you collect the data. So don't, this is maximum, this is good enough, this should be collected like a bandage of the range of the dose sample size. Again, we are not getting detailed to how to doing it, but we must understand why this is needed. Not always the more the better. You need to justify how small is small. Why small sample size dangerous? Why large sample size also dangerous? Right? Eventually, if you need to do it in a complicated model to a priori sample size determination, you just call me, I will do it for you. But making a decision is different story. Who do it at those in technical level is different story, right? If we start to taking a next class, and then we'll be getting into that, more details of sample size determination over time. All right, this is it for sampling design. Thank you.